In this video, we are looking at linear regression. So by way of introduction, remember we know how to draw the graph and find the equation of a linear function if we know f of a and f of c for two different inputs, a and c. The graph is the line that goes through the 2 points, a, f of a, and c, f of c. So what happens if we know f of a, f of c, and f of d for three different numbers, a, c, and d? In this case, if we want to find a straight line, we want to find a linear function whose graph goes through all 3 points, we may be out of luck. There may not be a line that goes through all 3 of the points, a, f of a, c, f of c, and d, f of d. So for example, let's suppose we are given that f of minus 1 is minus 2, f of 1 is 3, and f of 3 is 4. So this means that the graph goes through the points minus 1, minus 2, 1, 3, because f of 1 is 3, and 3, 4, since f of 3 is 4. Here are the 3 points, minus 1, minus 2, 1, 3, and 3, 4, and they do not lie on a single straight line. It will not be possible to find a linear function whose graph goes through all 3 of those points. But we could try to find a straight line that comes close to fitting the data given by these 3 points. Can't do it exactly, so we might be able to come close. When you have more than 2 points, as in the previous example, then finding a linear function that best fits the points is called linear regression. And that's what we're going to be doing for the remainder of this video. So if we're going to find the best linear function to fit given points, we will need some measure of how well a given linear function fits the data. We need some criteria for determining which function is best. And the usual way of measuring how well a linear function fits a collection of points in a coordinate plane is called the method of least squares. We'll look at the details of this method shortly. So as a first example, let's take the 3 points that we were looking at earlier, minus 1, minus 2, 1, 3, and 3, 4. And here is a linear function, which I picked more or less at random, just to have an example. And what I am about to do is calculate the least squares number that gives us a measure of how well this function fits these 3 points. So we're going to produce a number using the method of least squares, and this number will be a measure of how well this particular function fits these 3 points. If we took another linear function different from f of x equals 2x minus 1 and calculated in the same way that we're about to, we might get a different measure. So here are the points, minus 1, minus 2, 1, 3, and 3, 4. And here is the graph of the linear function, f of x equals 2x minus 1. And now we want to find some number that measures how well this graph fits the 3 data points. So what we're going to do is we're going to look at the vertical distances from each of the points, -1, -2, 1, 3, and 3, 4, to the line. So here are the vertical distances we will be looking at. The vertical distance from the point -1, -2 to the line, the vertical distance from the point 1, 3 to the line, and same kind of thing for vertical distance from 3, 4 to the line. So to get these vertical distances, we are going to subtract the height of the line from the height of the point. Let's look at the point 1, 3, for example. The height of the point 1, 3 is 3. Right? Remember, the second coordinate of a point tells you how high it is above the origin or above the x-axis. So the height of the point 1, 3 is 3. And we want to subtract the height of the graph of f of x equals 2x minus 1 at the point where x equals 1 from the height of the point 1, 3. How high is the graph of f of x at the point where x equals 1? Well, plugging in 1 will give us the height of the graph at x equals 1. If you replace x by 1 in the formula for f of x, you get 2 times 1 minus 1, which is 1. Height of the graph is 1, height of the point is 3. 3 minus 1 gives us the vertical distance from the point to the line. Okay, so here we are about to do the 3 calculations. So the first vertical distance is going to be the vertical distance from the point -1, -2 to the green line, the graph of f of x equals 2x minus 1. We are taking the y coordinate of the point, -2, and we are subtracting f of -1, the distance of the graph of the function from the x-axis when x is -1. We're doing 2 minus f of -1. If we plug -1 into the formula for f, we get 2 times -1 minus 1. So we'll be taking -2 minus a minus 3. And -2 minus a minus 3 is 1. Okay, for the second vertical distance, we are taking the height of the point, which is 3, at the second coordinate, which is 3, and we are subtracting the height of the graph, which is f of 1, the height of the graph above 1. 3 minus f of 1. If you plug 1 into the formula for f, you get 2 minus 1 equals 1. So we will be doing 3 minus 1, which is 2. And finally, for the point 3, 4, we will subtract the height of the graph from the height of the point. 4 minus f of 3. And what is f of 3? The height of the graph when x equals 3. Plugging 3 into the formula for f gives us 6 minus 1, which is 5. So we'll be calculating 4 minus 5, which is minus 1. So we have now calculated the three vertical distances of each of the 3 points from the graph. The first was 1, the second was 2, and the third was 1. And now the final step to get the least squares measure of how well this line fits the points. The final step is to square these distances, 1, 2, and minus 1, and add the results. So final step, square the vertical distances and add the squares. This number is called the sum of the squared deviations. So I will be having you calculate this in a few simple examples in the exercises. In this example, it would be 1 squared plus 2 squared plus minus 1 squared. Minus 1 squared is plus 1, so we would be adding 1 plus 4 plus 1 for a total of 6. This number 6 is our measure, is the method of least squares measure of how well the straight line that we were working with fits the 3 data points. And if we had started with a different linear function like 3x plus 1, the sum of the squared deviations probably would have been different. The best linear function for the data points using the least squares criteria is the linear function for which the sum of the squared deviations is smallest. So here in this displayed line, we calculated the sum of the squared deviations for our linear function f of x equals 2x minus 1 and got 6. What we are looking for is the best linear function according to this measure. There is probably a linear function for which the sum of the squared deviations is smaller. Before we get to the problem of finding the line for which the sum of the squared deviations is smallest, let's redo the calculations that we just did in the form of a table. This is the easiest way to do the calculations if you're going to do this on paper. Okay, so here's the table we will use. The 3 points, minus 1, minus 2, 1, 3, and 3, 4, appear in the first 2 spaces of each row. And now in the third column, we are going to calculate the height of the graph at the x value. So we are going to calculate f of minus 1 is what will go in this entry box. F of 1 will go in this entry box, and f of 3 will go in this entry box. So the third column, we're calculating f of x sub I to find the height of the graph of f above x sub I. Well, as we saw earlier, f of minus 1 is minus 3. F of 1 is 1. And f of 3 is 5. So we got these numbers by plugging in minus 1, 1, and 3 for x in the formula 2x minus 1. Now in the fourth column, we're going to calculate the vertical distances between the point whose coordinates appear in the first 2 columns and the point on the graph above x. It will be the y-coordinate of the point minus the height of the graph, which we calculated in column 3. Y sub I minus f of x sub I. So we're taking the entry in column 2 and subtracting the entry in column 3. Minus 2 minus a minus 3 is a plus 1. 3 minus 1 is a 2. And 4 minus 5 is a minus 1. And then finally, in column 5, we are going to square the numbers in column 4. 1 squared is 1, 2 squared is 4, minus 1 squared is plus 1. And then the final step is to add the numbers in column 5, and we get the sum of the squared deviations. It's 6, as we saw before, and it is our measure of how well the function 2x minus 1 fits the points. Let's try calculating the sum of the squared deviations for a different linear function using the same 3 points. So now I'm going to use the function f of x equals x plus 1. This I also chose more or less randomly, except that I wanted to use a fairly simple function. We will do this in table form, as we did before. So as before, the 3 points appear in the first 2 columns of the table, minus 1, minus 2, 1, 3, and 3, 4. In the third column, we calculate f of the x value. In other words, we plug the x value into the formula for f, which in this case is x plus 1. See, if x is minus 1, x plus 1 will be 0. If x is 1, x plus 1 will be 2. And if x is 3, x plus 1 will be 4. In the fourth column, as before, we take the value in column 2 and subtract the value in column 3. Minus 2 minus 0 is minus 2. 3 minus 2 is 1, and 4 minus 4 is 0. And then finally in column 5 we square the entries in column 4. Minus 2 squared is 4, 1 squared is 1, and 0 squared is 0. So the sum of the squared deviations is 5 in this case. That means that this function, f of x equals x plus 1, is a better fit than the function we considered before, f of x equals 2x minus 1. Because for f of x equals 2x minus 1, the sum of the squared deviations was 6. So here's a picture. Here are the 3 points, minus 1, minus 2, 1, 3, and 3, 4. Here is the first line, whose sum of the squared deviations we calculated. And here is the second line, f of x equals x plus 1. It's not obvious from the picture that the blue line is a better fit than the green line. But according to our calculations, it fits the 3 points better. The blue line fits better. And now we are moving to the problem of finding the linear function that fits the data best. We haven't done that yet for our 3 points. So when we find a linear function for which the sum of the squared deviations is smallest, we are doing linear regression. We will always do this using some kind of software. It is possible by hand, but it's sort of a tedious calculation. In our textbook, College Mathematics, in the reading for this module, there are detailed instructions for using a TI graphing calculator to do linear regression. In other words, given a set of data points, to find the linear function for which the sum of the squared deviations is smallest. But I'm going to be doing it on Desmos. I think this is easier. So let's go back to our 3 points. Minus 1, minus 2, 1, 3, and 3, 4. Here I have put them in a table. as we've done in several previous examples. And now step 1 for finding the linear function with the smallest sum of the squared deviations. Step 1, go to Desmos and click on the plus symbol that appears near the upper left corner. We'll see what this looks like in a screenshot shortly. So once you click on the plus symbol, a drop-down menu will appear, and from that menu we want to choose Table. Once you've chosen Table, in the calculation entry box, a table with headings x sub 1 and y sub 1 will appear. So here's what the Desmos screen looks like after doing the two things that I mentioned. First thing was to click on this plus appearing toward the upper left corner. From the drop-down menu, choose Table, and then this table appears in the first calculation box. Step 2. We want to enter the data points in the table. So the table on Desmos will look pretty much like the table with the data points that we just saw a couple of slides ago. So enter the points in the table. You can use the return key to go down in the table, and the tab key will move you to the right or to the next row if you happen to be at the end of a row. You can also navigate around the table using the arrow keys if you prefer. And as you're entering the data in the table, you'll notice that the corresponding points will appear on the graph that occupies the right 2/3 of the screen. Okay, step 3. In the next calculation box, below the calculation box that contains the table, enter the following thing: y sub 1 tilde m x sub 1 plus b. So there are a couple of things I want to say about this. The first is that the tilde symbol you can usually find at the top left of your keyboard. There is a key with both the tilde symbol and what's known as a backtick. The second thing I want to say is that when you are entering this, you don't have to worry about subscripts. You can simply type a y and then a 1, and then a tilde and an m, an x, a 1, a plus, and a b. And the subscripts will be worked out automatically. Once you have entered this in the second calculation box, the values of m and b will appear at the bottom of this calculation box. We'll look at a screenshot in just a minute. The value of m, in our case, is 1.5, and the value of b is 0.166667. And the graph of the function with slope 1.5 and y-intercept 0.166667 will appear on the set of coordinate axes on the right side of the screen. So all this happens automatically. Once you enter the y1 tilde mx1 plus b. And here is the screenshot after doing all of that. I have entered the numbers in the Desmos table. In the second calculation box, I have typed y1 tilde mx1 plus b. And now, appearing in this box are several numbers. For the moment, we are mainly interested in the value of m, which is 1.5, as I said before, and the value of b, which is 0.166667. These are the slope, 1.5, and the y-intercept of the linear function that fits the data best. So the best linear function for the three data points that we've been looking at for most of these slides is y equals 1.5x plus 0.166667, or f of x equals 1.5x plus 0.166667. There were two other numbers appearing in that second calculation box along with the m equals 1.5 and the value of b. The two other numbers were r squared, which was 0.871, and r, which was 0.9333. So the number r squared will always be a number between 0 and 1. And as you probably have guessed, you get the value of r squared by squaring the value of r. And this is supposed to be a measure of how well the best line, in our example, how well this line really fits the data. If r squared is close to 1, then we have a good fit. In our case, r squared is pretty close to 1. So our linear function, our best linear function, according to the least squares criteria, is a pretty good fit to the data. If r squared is close to 0, then it's probably not a good idea to try to fit a linear function to the data. You will get a function, a linear function. You'll get a value of m and a value of b, even if r squared is close to 0. But it's not a good approximation ordinarily for r squared values close to 0. Okay, I want to do one more calculation with the 3 points minus 1, minus 2, 1, 3, and 3, 4. So previously on these slides, not our last example, but in the two examples before, we used these 3 points and found the sum of the squared deviations for the two linear functions f of x equals 2x minus 1 and f of x equals x plus 1. And you may recall that the sum of the squared deviations for the first function was 6, and for the second function, for f of x equals x plus 1, the sum of the squared deviations was 5. That means f of x equals x plus 1 is a better fit than f of x equals 2x minus 1. But as we now know, f of x equals x plus 1 is not the best fit. So what I want to do in this example is take another random linear function and calculate the sum of the squared deviations for this new random linear function. But I want to do it using Desmos. I want to see how we can use Desmos to do this calculation and save some work. Okay, so our plan is to calculate the sum of the squared deviations for the linear function f of x equals 3x minus 2 using Desmos. So here on this next slide I've put the points and the formula for the function at the top of the screen, and now here are the steps. We'll see a screenshot shortly, but let's go through the steps first. Enter the points in a Desmos table, just like we did before. In the second calculation box, instead of entering y1 tilde mx1 plus b, use the value of m and the value of b from the linear function, 3x minus 2. So we're entering y1 tilde 3x1 minus 2. In the box where you entered the y1 tilde 3x1 minus 2, a button will appear, a plot button, and you should click on the plot button. Some new points will appear on the graph on the right-hand side of the screen, but we want to just ignore those new points. What we actually want to look at is the new column that appears in the table. As we'll see in the screenshot shortly, the numbers in this new column are 3, 2, and minus 3. These are the deviations. These are the numbers that we have to square and add the squares to get the sum of the squared deviations. So we take these three numbers, the deviations, we square them, and we add the squares to get the sum of the squared deviations. That would be 3 squared plus 2 squared plus a negative 3 squared. Looks like a 9 plus 4 plus 9, looks like a 22. The sum of the squared deviations for the linear function f of x equals 3x minus 2 is 22. Not a good fit for the data. Okay, here's the Desmos screen after doing those steps. So here, as before, in calculation box 1, I have entered the 3 points. In calculation box number 2, I have entered y1 tilde 3x1 minus 2. And here where the word residuals now appears was where the button labeled plot occurred. I clicked on the plot button, and this third column with entries 3, 2, minus 3 appeared in the table. These numbers are the deviations. To get the final answer, to get the sum of the squared deviations, I have to square each of these numbers and add the squares. This I have done in the calculation box number 3. And as we saw on the previous slide, 22 is the sum of the squared deviations. So just a reminder, in this last example, we were finding the sum of the squared deviations for a random linear function. We didn't have a really good reason for doing that because we had already found the best linear function. We just wanted to see how you could do that calculation on Desmos. In our next example, we're going back to finding the best straight line fit, the best linear function fit for given data. Here's the example. 6 patients at St. Joe's Hospital were selected randomly, and their weight, X sub I in kilograms, and their body fat content, y sub I. That should be, were measured. And the results are summarized in the following table. So at a weight of 84 kilograms, we had a body fat of 354. At a weight of 73 kilograms, body fat measure of 190, and so on. What I would like to do is find the linear function y equals mx plus b, or f of x equals mx plus b, that fits this data best. And as before, we're going to use Desmos to do this linear regression problem. So as before, we will enter the data in the first calculation box. In the second calculation box, we will type y1 tilde mx1 plus b. And after doing that, the Desmos screen looks like this. So here's the data entered in the table in the first calculation box. All that I have typed in the second calculation box is y1 tilde m x1 plus b. And what we are interested in, since we want the best linear function for the data, are the values of m, 1.54227, and b, 215.171. The slope and the y-intercept of the best linear function. Let's see, just taking a quick look at the graph here. The graph of the linear function with this slope and this y-intercept is the blue line. The points that you see are the data points on the graph, and it doesn't look like the best linear fit is too good a fit for the data. And that is reflected in this value of r squared. The value of r squared, 0.0114, is pretty close to 0. The data can probably not be fit very well by a linear function. We're going to ignore that fact for the time being. So m was 1.54227, and b was 215.171. So the linear function that fits the data best is f of x is 1.54227x plus b plus 215.171. So as we noted before, r squared is pretty close to 0, so this best linear function is probably not too good a fit. Okay, so here on the next slide, I have the function listed at the top, so it's available for us to use. And what I would like to do is, using this linear function, the one that best fits the data, I want to know what is the predicted body fat content of a person weighing 90 kilograms. In other words, assuming that this formula, f of x equals 1.54227x plus 215.171, gives the body fat of a person weighing x kilograms, or at least approximates it, what is the body fat of a person weighing 90 kilograms? We want to take the formula for f of x, and in the formula we want to replace x by 90. And as we've seen, when you do replacements like this, you frequently have to put the replacement number in parentheses. So this formula gives us as the body fat content for a person weighing 90 kilograms, 1.54227 times 90 plus 215.171, which is 353.973. And now one final example. An example having to do with the runway visual range. A brief explanation. So at airports, the runway visual range, which is RVR for short, is the distance in feet that a pilot can see down the runway. It's measured automatically by a device called a scatterometer. And measurements were taken over a period of several days at a large airport, comparing the RVR value, the runway visual range value, we'll use X for that, comparing that with the number of flights departing over a 15-minute time period. That will be our Y value. And the results of these measurements appear in the following table. So when the runway visual range was 0, in other words, when a pilot could not see at all down the runway, the number of departures per 15-minute period was 0. And the same if the RVR value was 200, 0 flight departures, and so on. The largest runway visual range number that was observed was 1,000 feet, and in that case the number of departures in a 15-minute period was 12. Okay, so the problem, part 1, we want to find the linear function that is the best approximation to the data. This is a pretty easy calculation using Desmos. So we'll use Desmos just like we did. So when the data is entered in a table, and y1 tilde mx1 plus b is entered in the second calculation box on Desmos, we get a screen that looks like this. Here's the table with the data entered. Here's the second calculation box, and the numbers we are interested in, since we're trying to find the best linear function, are the two numbers m, the slope of the best linear function, 0.0127481, and b, the y-intercept, minus 1.90331. So the equation for the best linear function for this data is f of x equals 0.0127481x minus 1.90331. And we see from the r squared value that this is probably a pretty good fit to the data. R squared is very close to 1. Okay, here is the least squares function, the best fit, the function for which the sum of the squared deviations is smallest. And I want to use it to approximate, first of all, the number of departing flights per 15-minute period if the RVR is 900 feet. So this was not one of the measurements taken. Well, this means that using this function, we have to replace x in the formula for f of x. Got to replace x in this formula by 900 in parentheses. And if we replace x by 900, we get f of 900, 0.0127481 times 900 minus 1.90331, 9.56998. So between 9 and 10 flights per 15-minute period when the RVR is 900 feet. That's what our function gives us. Secondly, I want to use our linear function to approximate the number of departing flights per 15-minute period if the RVR is 1,500 feet. So this is a little bit outside of the range of our observations. You remember that in our table, the largest RVR that appeared was 1,000. Well, this is just like the previous bullet. We're going to take the formula for f and replace x by 1,500 in parentheses. And when I do that and calculate, I get 17.21884 flights departing in a 15-minute period. And finally, I want to look at a really large value of the RVR, 10,000 feet. So this 10,000 feet is about the typical length of a of a runway at an international airport. So what does our linear function give us for the number of flights departing in a 15-minute period if the RVR is 10,000 feet? Replacing x in the formula by 10,000 gives us 125.5779. 125 or 126 flights per 15-minute period is what our linear function would give us for this large value of the RVR. Okay, problem part 3. What are the limitations of the model f of x equals 0.0127481 x, there should be an x in there, I'll have to correct that typo, minus 1.90331 for estimating the number of departing flights. This is not a perfect formula, and here are some things that came to mind. These are facts that are easy to find online. First of all, there are other factors besides the RVR that determine the number of departing flights. For example, wind speed, especially crosswind speed. The time of year affects the number of departing flights. And the amount of pilot training for flying under adverse conditions also affects whether or not a pilot can take off at a certain value of RVR. Secondly, as I said earlier, a typical runway at an international airport is about 10,000 feet. So all of the data that was collected was at a very low visibility. Right, the largest RVR value in the table was 1,000. So therefore the function that we found using these observations is likely not to be accurate at higher visibilities. And in particular, plugging in an RVR greater than 10,000 or so will probably give you a very unrealistic value. Finally, the number of departing flights in a 15-minute period at a typical international airport is normally smaller than 15 under ideal conditions. So when we use a value of 1400 for the RVR, you remember we got something like 17 flights in a 15-minute period. Plugging in any RVR value larger than 1400 will probably give us inaccurate results.